other than the sorry for this. Okay. So in the last class, we have seen about the Barkhasen criteria. That is the condition for sustained oscillations that we have seen it as a beta is greater than or equals to 1 that we have seen. And then after we have seen the classification of the oscillations we have seen. So basing upon the waveform, we have called output waveform, whichever we are going to be get, either sine waveform or non-sinusoidal waveform. So we call it as a sinusoidal oscillator, and as well as the non-sinusoidal oscillators we have been called. Uh, the sinusoidal oscillators which we get under this is like Hartley oscillator, Colpitt's oscillator, crystal oscillator, and as well as the RC oscillators. They comes under this sinusoidal oscillators. They come, and in the case of the non-sinusoidal oscillators, we have seen that which we it is going to be generate the waveform like a square wave or a rectangular wave or a triangular wave or tooth wave, whichever we are going to be get. We call it as a non-sinusoidal oscillator. And these non-sinusoidal oscillators are also known as relaxation oscillators, we used to call. Uh, some examples like under non-sinusoidal oscillators are multivibrators as well as the blocking oscillators we have seen. And as well as the classification of the oscillators basing upon the frequency also means the frequency which they are going to be generate. We have been classified in different types. One we call it as a audio frequency oscillators. Under these audio frequency oscillators, the oscillators which they are going to be produced the frequency in between 15 hertz to like 20 hertz to 20 kilohertz. We call it as audio frequency oscillators. We are going to be called, and we have another type like radio frequency oscillators. So these oscillators will generate the voltages in the frequency range. Of about 20 kilohertz to 30 kilohertz. That is greater than 20 kilohertz, it is going to be produced, which is 20 kilohertz to 30 megahertz, sorry. It is in between 20 kilohertz to 30 megahertz. Then we used to call it as a radio frequency oscillators we are going to be called. And another one which we get under this non type of frequency oscillators is ultra high frequency oscillators we call. So if the oscillators which they are going to be produce the uh, waves which are having the frequency greater than the 30 megahertz, we call it as a ultra high frequency oscillators we are going to be called. And these ultra high frequency oscillators are also known as microwave oscillators we are going to be called. So these are the classification of oscillators we have seen. And then after Barkhasen criteria, we have calculated like a beta is equals to 1, we have been calculated. And then after we have seen uh, we have started LC oscillators. Among that LC oscillators, we have seen about Hartley oscillator we have seen. So circuit diagram as well as the frequency of oscillations which it is going to be produced. The frequency we have been calculated, and then after we have seen all the how the phase shift will be there in these 180 degrees of phase shift you are going to get with the help of the tank circuit, and as well as the remaining 180 degrees of the phase shift it is going to be get with the help of the what we call transistor you are going to get. That is what we have seen in the last class. Now another type of LC oscillator is also is there that we call it as a Colpitt's oscillator. So today we are going to be see about this Colpitt's oscillator. Just share the screen. Right. So today we are going to be study about Colpitt's oscillator. So it is So Colpitt's oscillator is essentially the same as a Hartley oscillator, except for one difference. So instead of using tapped inductance, Colpitt's oscillator uses tapped capacitance. So that is what we have the difference. So by drawing the circuit diagram, we'll be knowing that one. So here we'll draw the circuit diagram of this Colpitt's oscillator. First, we'll draw the this transistor. This is a base. This is one is a collector, and this is a emitter. We are using NPN transistor here. So for this emitter, we are going to be connect a resistance, which we call it as a emitter resistance. And for this, in parallel to this resistance, we are going to connect a capacitor here. And this combination is going to be connected to ground. And for this collector, again, we are going to connect a RFC, a radio frequency choke. This is a RFC. And for this base, we are going to connect a resistance here, which is a R1. Generally, we call it as a dividable resistance. So R1. And this combination, we will be connecting to a power supply with a key here, which is a plus VCC. Plus VCC. And here we have a feedback circuit to the tank circuit. This is the capacitor C dash. And this resistance here, another resistance. This one, which is a R2 here. Then after, from the collector, we have to connect another capacitor, C double dash. And from this feedback, you are going to be get. And here we have the tank circuit with a combination of two capacitors. It's connected to a inductor here. And this is feedback which you are going to get. And this will be connected to input here. That is a input base connected capacitor C dash. So this resistance we named it as a RE, and this capacitor is a CB, and this capacitor is C1, this capacitor is C2, and the inductor is here L we have. So this is one terminal, second terminal. Second terminal. Here we have the third terminal, which we are connected here. Right. So this is what the circuit diagram of Colpitt's oscillator. So if you observe the circuit diagram of the Colpitt's oscillator, so it is almost the same as a Hartley oscillator, except for one difference. That is, instead of using tapped inductance here, we are using in the Colpitt's oscillator as a tapped capacitance we are going to be used. So here the capacitors C1 and as well as C2 are placed across a common inductor L here. and the center of the two capacitors is tapped in as shown in this figure. Okay, center of these two capacitors is tapped as shown in the figure here in the circuit diagram. So here we have different resistors and capacitors. Suppose if you see the resistors here, R1 and R2. So these two resistors, R1, R2, form a voltage divider across the supply voltage VCC here and provides a necessary bias condition for the circuit along with this emitter resistor RE, right? So, and the remaining capacitors, if you see here, so we have this capacitor C double dash. So this function of the capacitor C double dash is to block DC and provides an AC path from collector to the tank circuit here. So as we have seen in the case of the Hartley oscillator also, this same capacitor you are going to be have this C double dash capacitor, which will blocks the DC and it is going to be provide AC path from collector to this tank circuit here. And this radio frequency choke RFC, which provides necessary DC load resistance for the collector and also which prevents the AC signal from this entering the DC here. So this RFC radio frequency chip provides necessary DC load resistance for a collector and it also prevents the AC signal from entering the DC. Okay. So now the circuit operation, if you see here, so now this supply voltage SVCC, this supply voltage VCC we have connected. So, and this capacitor CE is a bypass capacitor, and we have another capacitor C dash. So this C dash conveys feedback from the collector to which conveys the feedback from the collector to base circuit, which is going to be have. So these are the components which are involved in the circuit diagram of the Colpitt's oscillator. So if you see the difference between the Hartley oscillator and Colpitt's oscillator is only this tank circuit. Here the inductors are replaced by the capacitors C1 and C2, and this a capacitor is replaced by an inductor L. So that is what difference you have. All the remaining whatever may be the resistors or capacitors, you are going to be have the same as in the case of the Hartley oscillator which we have. Now, if you see the circuit operation, so now when the collector supply voltage VCC is switched on by closing this key. So whenever that means whenever we will supply this supply voltage VCC, then what will happens means here, whenever it is going to be supplied. So initial case, what it is going to be happens is initially the capacitors C1 and as well as the capacitor C2. So both the capacitors C1 and C2 are going to be charged here. So that is whenever we connect this power supply VCC through this capacitor C double dash, it is going to be give AC part, and here this C1 and C2 capacitors are going to be charged fully. So once the capacitors C1 and C2, whenever they have been charged, so whenever they have been charged fully, so after this is C2, we have, okay. So whenever these capacitors C1 and C2 are charged fully, so these capacitors starts discharging through this inductor coil L. Okay, so whenever they are going to be charged fully, they are going to be discharging through the inductor coil L, which is setting up some damped harmonic oscillations in the tank circuit. Understand? So after completely charging these capacitors, they are going to be discharging through this inductor coil, which is going to be set up the damped harmonic oscillations in the tank circuit. That you have to remember. So once after that is done, so this oscillatory current in the tank circuit, which is going to be produce an AC voltage across C1 here. So it is going to be produce the AC voltages. That is alternating current voltages. It is going to be produced across C1. So which is applied which is applied to the what we call a base emitter junction. So that means that the input it is going to be applied here. So once the key is switched on, the capacitors are going to be charged fully. C1 and C2 capacitors are going to be charged fully. Then it is going to be discharged through this inductor, which is going to be make some oscillatory current in the tank circuit, which is going to be produce an AC voltage across C1. And this C1, which is applied to the base emitter junction. So this is the base emitter junction, which is going to which we are going to be apply this oscillations of the transistor, and they are amplified form in the collector circuit, which is going to get off. Okay, once it is given as an input for this one from the output, which is going to be get it as an amplified form in the collector circuit, that is the collector emitter circuit. Okay, and overcomes the losses occurring in the tank circuit. Right. So now you can see this that the energy supplied to the tank circuit here, the energy supplied to the tank circuit is in phase with the generated oscillations. Okay, the energy supplied to the tank circuit is in phase with the generated oscillations in this tank circuit. So the feedback voltage, that is a voltage across C1, whichever we are going to be have. So the feedback across the voltage, sorry, the feedback voltage, which is across the capacitor C1, it is going to be 180 degrees out of phase. It is going to be 180 degrees out of phase with the output voltage. That is voltage across capacitor C2. So now it is because the terminal 3 here, the terminal 3 here is earth, which will be at a zero potential. So when one is at positive potential with respect to this 2 and 3, will be at negative potential with respect to 3. Okay. When one is positive potential with respect to 3 here, and 2 will be at a negative potential with respect to 3 here, it is going to be half. Therefore, this point 1 here, whichever we have, and point 2, these two are out of phase of 180 degrees. 180 degrees out of phase they are going to be have. They are 180 degrees out of phase. That you have to remember. Right. So 180 degrees out of phase. Then after a further phase shift of 180 degrees is going to be takes place between the output and input voltages, which are produced by this common emitter transistor. So 180 degrees out of phase is in between the C1 and C2 capacitors. The remaining 180 degrees, which is going to be produced between the output and input voltages of this common emitter transistor. So therefore, 180 degrees of phase out of phase between these capacitors C1 and C2 you are going to be have, and the remaining 180 degrees of out of this phase shift you are going to be get this phase shift you are going to be get in between output and input of the transistor, input and output of the transistor. So here 180 degrees of phase shift you are going to be produced. So therefore, this 180 degrees and this 180 degrees total 360 degrees of phase shift or zero phase shift you are going to produce. So that is the phase shift condition for sustained oscillations is satisfied, and we get continuous undamped oscillations you are going to get. So this is what we have the circuit operation for the Colpitts oscillator. So once again, if you see the circuit operation for this Colpitts oscillator. So initially what we have to do is we have to supply this, we have to connect this key to this VCC so that the voltage, DC voltage is going to be get here, and this C double dash is going to be give AC component, which is going to be supplied this energy to this tank circuit here. So whenever you are supplying this energy to the tank circuit, these capacitors C1 and C2 are going to be charged fully. Once they have been charged fully, they are going to be discharged through this coil, that is an inductor L here. So this is going to be produce this what we call a sine waveforms. Otherwise, AC waveforms it is going to be produced here. It is going to be generate this oscillations. It is going to be generate. So once the generated oscillations their AC, which is going to be given to the input of this transistor, that is from the capacitor C1 to this input of the transistor, that is a base emitter junction. And after that, the amplified signal is going to be get out from the output, that is through the collector emitter terminal you are going to be get here. So in this case, the C1 and C2 are out of phase of 180 degrees. So 180 degrees of out of phase here it is going to be present. Then after 180 degrees of phase shift is going to be get in between the this output and input of the transistor. That is a collector emitter output transistor and a base emitter junction in this input transistor. So total 180 degrees plus 180 degrees, 360 degrees of phase shift or a zero phase shift it is going to be produced. From that we can get the sustained oscillations you are going to be get. Otherwise, continuous undamped oscillations you are going to be get. So this is what we have the circuit operation. So once after this circuit operation, we have to derive the frequency of oscillations in the case of the Colpitt's oscillator we have to derive. So in order to derive this frequency of the oscillations, as we have seen in the case of the what we call in the last class, whichever we have seen in the case of Hartley oscillator, the mathematical equations, whichever we have seen. So we have to get the equivalent circuit of this Colpitt's oscillator, which is similar to Hartley oscillator, which we have seen in the last class. You are going to be get here. So then after getting that one, so we can derive a mathematical equation which we have derived in the Hartley oscillator. So we are going to be get this equation, so which is in the form of HIE. We are writing the H parameters of that one. So Z1 plus Z2 plus Z3, HIE into Z1 plus Z2 plus Z3 plus Z1 Z2 into 1 plus H of E you have. So then after plus Z1 Z3 is equal to 0. So this is the equation which we can get with the help of the equivalent circuit of this Colpitt's oscillator. So this equation you are going to get. So here we know that the Z1, Z2 and Z3 are the impedances which we are going to be have. So in the circuit, like otherwise we can say that these are the Z1, Z2, Z3 are either capacitive impedances or inductive impedances you are going to be have. Okay. So once after getting this equation, so what we have to do is we have to find the frequency of oscillations so we have to get here. So after this, by neglecting the inductor resistance, so especially we can write the Z1 value. So Z1 is equals to, we can get it as in the case of the capacitor as 1 by J omega C1 we can get. So this also can be written as minus J by omega C1 we can write. So this is in the case of the Z1. And similarly, we will write Z2 value also. So Z2 is nothing but 1 by J omega C2. So which will be equals to minus J by omega C2 you are going to get. And similarly, we can get the value of Z3. So this Z3, which is equals to, in the case of the inductors, so it is J omega L we have. So we have got Z1 is equals to minus J by omega C1. Z2 is equals to minus J by omega C2, and as well as Z3 is equals to J omega L we have got. So these values, Z1, Z2, Z3 values, we will substitute in this equation 1 here. Okay, so in this equation 1, we have going to substitute. So once if you substitute, so here first what we have here it is HIE is there, HIE into Z1 plus Z2 plus Z3 is there. So here HIE H I E into Z1. Z1 we have got it as a minus J by omega C1 plus Z2, which is minus J by omega C2 plus J omega L. First part of this equation. So we'll write here, we'll check here. So HIE into Z1 plus Z2 plus Z3, HIE into Z1 plus we have written minus J by omega C1 minus J omega by minus J by omega C2 plus Z J omega L we have written here. So then after next, what we have is plus Z1, Z2. So here we'll write plus Z1, Z2. So Z1 is nothing but minus J by omega C1 into Z2. Z2 is minus J by omega C2 we have. Right. So into what we have here, it is into 1 plus HFE. So here into, we'll write here into 1 plus HFE here we are. And then after, next what we have here, it is into Z plus Z1, Z3 is there. So here we'll write plus Z1. Z1 is nothing but minus J by omega C1 into Z3 is J omega L, which will be equals to 0 here. So we have substituted all the Z1, Z2, Z3 values in the equation 1. So we have written this equation. Now, if you solve here this equation, so first we'll take uh, this minus J outside. So we'll get minus J, HIE we'll get here. And then after it will be 1 by omega C1 plus 1 by omega C2 minus omega L here we have, right? So minus omega L. Then after in this, we take, we have taken J in this second one, so minus. So we will get it as omega C1, omega C2 is there. So it will be omega square C1, C2. J is taken common in all the cases we have taken outside. So here we'll get omega square C1, C2. So first case, we'll get it as, here it will be 1, here also 1. Here in this case, HF is there. So overall, you are going to get 1 plus HF E you are going to get. Plus last one, we have taken minus J outside, so it will be plus. We have a here we have omega will get cancels here, this one and this one. So we are going to get it as L by C1, which will be equals to 0. So this one we get, and further solving this one, so we can get it as 1 plus H of E divided by omega square C1, C2 plus L by C1, L by C1 plus, here we will write it as a J, the first term whichever we have, we are writing J H I E, and in brackets we can get it as a J by omega C1 plus J by omega C2 minus omega L, which will be equals to 0. So this is what equation which we get. We are writing it as equation 2. So then after getting this equation, what we have to do is we have to equate the imaginary part on both sides of this above equation. So equating the imaginary part on both sides of equation 2 here. So then we'll get if we equate the imaginary part, we get it as j by omega c1 plus j by omega c2 minus omega L is equals to 0 we'll get here. So from this, what we are going to get is, so if you take here in the denominator, it will be omega square c1 c2, omega square c1 c2. In the here we'll get it as c1 plus c2 minus omega L, I'm writing as it is, which will be equals to 0. So this is the equation number 3. Now from this, we can get the what we call omega value. So what we have got here, it is c1 plus c2 by omega square c1 c2. So here omega c1 plus c2 by omega square c1 c2. So which will be equals to omega L. So here it will be omega L we are going to get. So C1 plus C2 is equals to what you'll get? Omega square omega. Sorry, here it is not omega square. It is only omega. So we have taken LCM of omega C1 and omega C2. So here we'll get only this C1 only, omega C1, C2. So it will be C1 plus C2 by not omega square here is omega. So omega, it is omega C1, C2 will be. So therefore, from this, we can write it as C1 plus C2, which will be equals to omega square L C1 C2 we get. So from this, we can write omega square, which will be equals to C1 plus C2 by C1 C2 we get. So from that, we can write omega. So L will be there here, sorry. L will be there. So it will be omega, which will be equals to root of C1 plus C2 by root of C1, C2. Otherwise, you can write this as equals to 1 by root L separately, and this is C1 plus C2 by C1, C2 we can write. So we know that omega is nothing but the frequency of oscillations. Sorry, omega is nothing but 2 pi f we have. Since omega is equals to 2 pi f, that implies f is equals to 1 by 2 pi. This if you write here, C1 plus C2 by LC1 C2. Okay. So LC1 C2. So this is the frequency of oscillations for Colpitt's oscillator. This equation number 4, which we have got here, it is F is equals to 1 by root 2 pi 1 by 2 pi into root of C1 plus C2 by LC1 C2. So this condition is called it as a frequency of oscillation. Otherwise, we can call it as a condition of maintenance of oscillations we are going to be called here. So this is what Colpitt's oscillator frequency, which we are going to be have. So by equating the imaginary part, we have got a condition of maintenance of oscillations we have got. Now next, in this equation, we will make equal both sides. That is, the real parts on both sides of this equation too, we are going to be equate. So now after this, obtaining this condition of maintenance of oscillations, now we will equating the real parts on both sides in equation number 2. Equating the real parts, equating the real parts on both sides, of equation 2. Equation 2 is here we have. So this is equation 2. In this we have to equate both real parts. So if we equate, what we have here is we have 1 plus HFE by omega square C1 C2, and this is L minus LC1 we are going to get here. So that is 1 plus HFE by omega square C1 C2 minus L by C1, which will be equals to 0. So from this, you can write 1 plus HFE by omega square C1 C2 is equals to L by C1, we can write. So from this, you can write the 1 plus HFE value, which will be equals to omega square C1 C2 L by here we have 1 plus HFE. 1 plus HFE is equals to omega square C1 C2 L by C1 here. 1 plus HFE is equals to omega square C1 C2 L by C1 we have got. Now substituting the value of omega square L C1 C2 from this equation. So here we have got omega square C1 C2 value, whichever we have got here also. So here we do. So here we have this equation. Okay. So I'll round it down so that it is easy to see. So we have this omega square L1 C1 C2 is equal to this one. So this value here we'll substitute. So substituting the value of omega square C1 C2 L from the above, if you substitute, we can get it as 1 plus HFE is equals to 1 plus HFE, which will be equals to what we have omega square C1 C2 L, we have it as a C1 plus C2 by C1. So which we can write it as a 1 plus C2 by C1 also we can write. So therefore, Therefore, we can get this 1 plus HFE is equals to 1 plus HFE, which we are getting as 1 plus C1 by C2 we have got. So therefore, HFE, which we are going to get it as a C1 by C2. Okay. HFE is equals to C1 by C2 we have got. So this HFE is equals to C1 by C2 equation, whichever we have got here. This is equation number 5, I think. So this gives the condition of sustained oscillations in Colpitt's oscillator. So the circuit can be adjusted for oscillations by varying the C1 and C2 value. So we can adjust the oscillations. So these are for Colpitt's oscillator. So Colpitt's oscillator here, once we see. So we have Colpitt's oscillator as similar as the Hartley oscillator. Only the thing is, in the case of the tank circuit here, in the case of the tank circuit, there the inductors has been replaced by these capacitors here. So in this tank circuit, in the case of the Hartley oscillators, inductors are replaced by the capacitor C1 and C2, and their capacitor is replaced here by a inductor coil L. So that is only difference we have in the case of the circuit diagram of the Colpitt's oscillator as well as the Hartley oscillator. So we have, if you see the different components in the case of the Colpitt's oscillators, R1, R2, RE are nothing but the dividing resistors, which will keep this oscillator into a operating point. And here C double dash, which is going to be prevents DC, and it is going to be gives AC signal, and which is supplied to the tank circuit. So once the which is C double dash is giving energy to this tank circuit, these capacitors C1 and C2 both are going to be charged fully. So once it has been charged fully, it will be discharges through the coil C1, and then you are going to be make these oscillations, sustained oscillations you are going to make it, and these oscillations will be given as an input to this base emitter junction of the transistor, and so that output will be getting in the collector emitter junction as amplified signal. So that amplified signal you are going to be get. So now if you see about the phase shift, so there will be a phase difference between these capacitors C1 and C2, which are 180 degrees of out of phase with the applied signal. So 180 degrees out of phase, you are going to be get the help of this C1 and C2. And the remaining 180 degrees of phase shift you are going to get in between these two input and output of this transistor. So that is base emitter junction as input and collector emitter junction as output. So you get 180 degrees more phase shift in these two you are going to get. So therefore, the total phase shift in this case is 360 degrees or 0 degrees, which is going to be produce sustained oscillations here. Okay. So the phase shift condition for sustained oscillations is satisfied, and it is going to be give continuous undamped oscillations it is going to be give. So then after, as we have seen in the case of the Hartley oscillator, we will write the equivalent circuit of this Colpitt's oscillator, and from that we are going to get different impedances like Z1, Z2, Z3 impedances you are going to be get. So Z1, so the final equation by neglecting some parameters, so we'll get this equation. So that is HIE into Z1 plus Z2 plus Z3 plus Z1 Z2 into 1 plus HFE plus Z1 Z3 is equal to 0. So this equation already we have been derived in the case of the Hartley oscillator. So this equation you are going to get. So then here we will apply this impedances Z1, Z2, Z3. So Z1 is nothing but we can write it as a 1 by j omega C1, which we can write it as a minus j by omega C1. Then after we'll write Z2 is equals to 1 by j omega C2, which we can write it as a minus j by omega C2. and Z3 is equals to J omega L. These three values we are going to derive. Then after substituting the values of these Z1, Z2, Z3 in the equation 1, so we will substituting and rewriting, we'll get this equation number 2. Here we are going to get this one. This equation we are going to get here. So by substituting all the Z1, Z2, Z3 values here. There. Then after what we'll do is we will equate the imaginary part in this equation we are going to be equate, so that we get in this equation. So if we equate the imaginary part, we have got like a J by omega C1 plus J by omega C2 minus omega L. So which we can get it as a C1 plus C2 by omega C1 C2 minus omega L. So from that we can get the value of omega L we can get. So then we get the omega square. So omega is nothing but angular frequency, which is equal to 2 pi. By substituting that, we get the F value as 1 by 2 pi under root of uh, C1 plus C2 by L C1 C2. So this F, which we have got 1 by 2 pi under root of C1 plus C2 by L C1 C2, is the frequency of oscillations. Okay, this is a condition for frequency of oscillations we are going to get in the case of the Colpitts oscillator. Now, in order to get the condition of maintenance of oscillations, which is obtained by equating the real parts on both sides of the equation 1, which we have written here. So equation 2, I think. So by equating this one in this equation, we will equating the real parts on both sides, so that we'll get it as this 1 plus HFE by omega square C1 C2 minus L by C1 is equals to 0. We are going to get. So then after rewriting, we will get the value as 1 plus HFE is equals to omega square C1 C2 L by C1 you are going to get. So from this, we will have in the denominator like omega square C1 C2 L. So this value we can get from here. So we got omega square L C1 C2 as C1 plus C2. So we will substitute the value of omega square C1 C2 L in this above equation, so that we have got 1 plus HF is equals to 1 plus HF is equals to C1 plus C2 by C1, which we have got it as 1 plus C2 by C1. So which from that we can get the value of HF is equals to C1 C2. HF is equals to C1 by C2 we have got. So this gives the condition of sustained oscillations in Colpitts oscillator you are going to be have. Okay. So then, so this is what about uh, LC oscillators, both what we call Hartley oscillator as well as the Colpitts oscillator, both oscillators we have seen. So then after just we'll discuss about the phase shift oscillator. In the next class, we'll see full-fledged about the phase shift oscillator. Next, we'll see what is a phase shift oscillator and what type of wave we are going to get. Briefly, we'll discuss about this one. Phase shift oscillator. Phase shift oscillator. Yeah, right. So this phase shift oscillator, if you consider, so this phase shift oscillator, tuned circuits are not essentially required for producing oscillations. So what is essential we required is that there should be a feedback of energy from output to the input in proper phase to overcome the circuit losses and maintain oscillations. So as we know that, so this is what if you have a circuit, this is the input and this is the output, whichever we have. So we can take some part of the output as a input, which we call it as a feedback here. Already we have seen. So this input will be there, and this is the output. So input, and this is what we have the amplifier circuit. So here, what is the essential thing, which is that there should be a feedback of energy from output to the input in proper phase to overcome the circuit losses and to maintain oscillations that you have to do. So it can be obtained by employing the resistive and capacitive oscillations. Resistive and capacitor, the thing whichever we have, that can be obtained with the help of the RC combination. That is nothing but the resistive and capacitive oscillations. So such oscillators using this what we call a RC feedback network, which are called it as a RC or phase shift oscillators. We are going to be called here. We call it as a RC oscillators. We are going to be called. So in the case of the RC oscillators, we have like two different types of oscillators we have here. So we can get in the case of the RC oscillators as one is as we have seen, which we call it as a RC phase shift oscillator. We are going to be called. So this comes under the RC oscillator. RC phase shift oscillator will comes under the RC phase shift oscillator, and as well as one more we have is uh, Wien bridge oscillator. So this Wien bridge oscillator also works under the same uh, formula, that is RC oscillator. So these RC phase shift oscillator or a Wien bridge oscillator, both these oscillators are comes under what we call sinusoidal oscillator. The output which is generated output already we have seen classification of these oscillators we have seen the output of these oscillators, these both oscillators, if you take, so these both oscillators output, if you see here, so these you are going to get another output which you are going to get is a sine waveform, so that these oscillators are also called it as a sinusoidal oscillators we are going to be called. So these comes under the RC phase shift oscillator as well as the Wien bridge oscillators. Both comes under what we call sinusoidal oscillators only we are going to begin. So in detail about like RC phase shift oscillator, we'll see in the next class we are going to be see here. Yeah. So these RC phase shift oscillator and as well as Wien bridge oscillator we'll see in the next coming class.